A large part of the world population, from highly populated cities to rural villages, is seriously vulnerable to the effects of natural hazards. In particular, losses due to earthquakes constitute a significant part of the global losses due to natural hazards, and are those that cause the highest number of casualties. For example, about 20% of Europeans live in areas with a moderate to high seismic hazard. In addition to high loss of human lives, earthquakes are also responsible for significant loss in cultural heritage assets, the most vulnerable and valuable constructions. Recent earthquakes have demonstrated a strict correlation among safety of citizens, loss of cultural heritage value, and increased danger caused by incorrect interventions on buildings. Earthquakes are unpredictable and inevitable, but the loss caused can be minimized. Together with a suitable characterization of the seismic hazard, the main tool to mitigate casualties and protect cultural heritage assets is the development of materials and technologies aimed at reducing the structural vulnerability of the constructions to earthquakes. Potential damages on cultural heritage assets are currently too high, mostly due to their intrinsic vulnerability and to the fact that most of the materials and technologies applied to date are too intrusive, cost inefficient, and often unreliable or non-effective. NIKER is a research project funded by the European Commission, aimed at the protection of cultural heritage from earthquake-induced risk. The NIKER project encompasses the active participation of 18 partners, representatives of universities, research centers, public organizations, and private companies from 12 countries of Europe and the Mediterranean basin. The project tackles the problem of earthquake impact on cultural heritage assets, starting from consideration that efficient protection can only be achieved on the basis of the minimum intervention approach. This requires that the potentials of existing materials and components are exploited as much as possible, and that candidate interventions are validated and optimized under real-life conditions. The project is organized into 10 interactive work packages. Its main objective is the development and validation of innovative materials and technologies for systemic improvement of seismic behavior of cultural heritage assets. To reach this goal, the project is structured into 3 main steps. Creation of a database with new relational structure with the task of orienting and assisting the development of materials and techniques for intervention. Experimental testing, numerical simulation, parametric modeling, and derivation of design methods for vertical and horizontal structural methods and connections, and for the overall seismic behavior of buildings. Development of knowledge-based assessment procedures, validation of the entire methodology on real case studies, and development of guidelines for end users. The first step of the project deals with the studying of available classifications and databases on earthquake-induced failure mechanisms, construction types and materials, interventions and assessment techniques in order to cross-correlate the information already available in literature. Cultural heritage construction typologies and the related structural elements are listed and associated with the most significant failure mechanisms for each structural element. The main outcome of the catalogue is a matrix that connects the available intervention techniques with the elements on which they are applicable and the related failure mechanisms that can be hindered or reduced. This relational structure also provides the performance indicators of the strengthening techniques when these are available in literature or from the tests carried out within the project. The overall seismic response of historic buildings is determined by the behavior of the single structural vertical and horizontal elements, as well as by their mutual connections. The experimental activities within the NIKER project include testing of vertical elements, testing of horizontal diaphragms, testing of structural connections, shaking table testing of substructures and building models. The experimental tests on vertical elements were carried out on stone, brick, earthen and timber-framed masonry walls. Tests were also carried out on real walls on site. The The construction techniques for stone masonry consisted essentially in regular and irregular three-leaf limestone masonry. Adobe walls were constructed as one-leaf masonry with earthen mortar. Rammed earth specimens were prepared by hand with formwork. Cob specimens consisted of a mixture of raw earth and straw. The timber-framed panels consisted of timber and clay brick masonry. Different types of strengthening were considered, ranging from traditional to innovative techniques and materials. The static and cyclic tests carried out encompassed uniaxial compression tests, diagonal compression tests, and shear compression tests, in order to get a comprehensive characterization of basic mechanical properties and of seismic performance of the masonry walls with and without retrofitting. The experimental tests on horizontal diaphragms were mainly aimed at characterizing the in-plane stiffness of wooden floors, the formation of a four-hinge collapse mechanism in brick masonry vaults, and the cyclic behavior of roof wooden frames. The in-plane monotonic and cyclic tests on wooden floors were carried out on both reconstructed wooden floor specimens and on-site bare wood or trodden earth floor specimens. Various strengthening techniques were applied. The brick masonry arches were tested under monotonic and fatigue loading, with intrados and extrados SRP strengthening. Cyclic tests were carried out on brick masonry vaults before and after strengthening by various types of fiber-based composite materials. A series of tests were carried out on wooden trusses rescued from existing buildings, also in relation with the deterioration of the connections, and the physical and mechanical characterization of wooden materials in timber elements. The tests on structural connections included single structural elements, whole connections, and entire structures. The types of tested connections covered connections between masonry walls, connections between traditional masonry walls and timber floors, wall-to-wall and wall-floor roof connections in different earthen materials, dovetail halved joints of roof frames, connection between the leaves of multi-leaf stone masonry walls. The shaking table test program included tests on substructures at real scale and tests on building models at reduced scale. The experimental work on substructures covered the cases of shaking table testing of walls under out-of-plane excitation, shaking table testing of a brick cross vault supported by two three-leaf stone masonry walls. The tests on model buildings included 4 specimens made of three-leaf stone masonry with timber floors in as-built condition, after grout injections of the walls and with enhancement of the diaphragm action. The structural analysis of an historical construction contributes to a better understanding of its current condition, helps to elaborate a reliable diagnosis, and makes possible to numerically test and optimize the design of intervention measures. However, the modeling strategies to be adopted depend on the complexity of the structure, level of accuracy required, availability of input data, and use of the results. The numerical modeling inside NIKER was carried out at 2 main levels. Complex numerical strategies were adopted to simulate the experimental tests and to give adequate insight to the test results. These detailed models were used to carry out parametric analysis necessary to define critical mechanical parameters, to assess the performance of the proposed intervention techniques, and to assist the tasks of optimizing design. These models were also used to derive simplified relationships to be applied in the analysis of entire buildings. Hence, parametric study of buildings when varying their main features and strengthening options was carried out. In this way, the building performance and response parameters to be used in seismic assessment and performance-based design were identified. The seismic assessment procedure proposed within NIKER involves a series of activities, such as inspection, monitoring, structural analysis, intervention, and quality verification systems. The application of knowledge-based assessment procedures to case studies is intended to validate the entire integrated methodology in real site conditions and involves calibration of monitoring systems and devices, application of the monitoring systems and devices for the identification of the real behavior of buildings, application of the knowledge obtained through monitoring to the creation and updating of reliable structural models, definition, evaluation, and implementation of optimal intervention techniques, implementation of instrumented dissipative devices, assessment of the effectiveness of interventions through optimal quality assessment procedures. The selection of 20 case studies was intended to cover a wide and representative range of conditions regarding geographical location, local seismic hazard, construction materials, structural typologies and uses, preservation condition, and risks involved. Among the buildings considered are a set of churches, a large fortress, a large Roman construction, masonry towers and minarets, large Gothic cathedrals and monasteries, masonry buildings, a former Byzantine church, and a large earthen construction. All these cases have been analyzed and evaluated regarding their potential contribution to the validation of the monitoring systems and model updating strategies resulting from the project. Some of them are also considered for the implementation and validation of intervention techniques, along with the application of the quality assessment procedures. The guidelines for end users with practical information for the protection of cultural heritage assets from earthquake-induced risks are a major result of the NIKER project. The guidelines developed characterize the design and execution of innovative intervention technologies on vertical and horizontal elements. The various techniques described in the documents present details on materials, design rules, and relation with possible failure mechanisms and damages. The guidelines suggest also optimum intervention for improvement of seismic performance of vertical and horizontal elements. Furthermore, a set of dissipative devices have been developed and validated. The guidelines provide recommendations for a correct choice, optimum design, and installation of dissipative systems. The multidisciplinary nature of interventions on cultural heritage presents a high complexity for professionals to achieve the necessary knowledge to support the making of decisions. In this sense, the procedure required to support and control an adequate decision-making process aimed at the selection of correct interventions is also addressed in the guidelines. The preservation and valorization of architectural heritage is more and more a major social and economic concern in modern societies. The research work carried out within the NIKER project represents a valuable contribution to characterize and to improve the seismic performance of cultural heritage assets, and thus to protect them from earthquake-induced risks. As cultural heritage buildings are part of our identity, we are responsible for keeping them in good condition for the generations to come.